So last class we defined attention, and as we learned, we only fully process sensory information that we attend to, especially when the task at hand is demanding. So this is as predicted by perceptual load theory. So being able to shift attention is really important. As William James noted, attention implies withdraw from some things in order to deal effectively with others. So how do we do that? That's what we're going to look at in this lecture. How do we shift our attention? This lecture is based on chapter 4 in your textbook. So first of all, we can shift attention overtly or covertly. In this case, we're talking about visual attention, and so overt shifts in visual attention mean moving the eyes. So we can move the eyes move via saccades, so jumps from one location in space to another. And these jumps reflect an overt shift in attention. We can also covertly shift attention, right? So you can shift what you're attending to without moving the eyes. You can effectively attend to things in your visual field that you aren't directly working at, right? So I can ask you to stare at this cross and have you, keeping your eyes fixed on the cross, shift your attention either to the right or to the left. So when we initially encounter a new scene, we want to put interesting images onto our fovea. And so we scan the scene. And we can look at how people fixate when they're looking at new scenes by tracking eye movements. Actually, we have eye tracking here at Acadia. And so eye tracking devices simply look at where the eyes jump around a scene when they first look at it. And so in this image here, we can see the scan path of somebody who is seeing the scene for the first time. And what you'll notice is that, they're looking at things that are interesting, right? They're looking at things that they probably want to perceive. They're shifting their attention towards things that are new and interesting. They're not spending a lot of time, for instance, just staring at the sky or attending to the sky. And there are a variety of reasons for that. And this is because we sort of know that, the sky is just not a really interesting thing to look at. So shifts in attention based on eye movements, overt shifts in attention, can be driven by both bottom-up information, right, and top-down information. So if we're talking about bottom-up drivers of attentional shifts, we're referring to the physical properties of scenes, the physical properties of stimuli in scenes. And so initial fixations are often driven by the salience of items in a scene. So if you look at, for instance, this scene here, probably the most salient feature of this scene is the border between the beach and the ocean. And so when individuals first look at this scene, their eyes tend to shift towards features like this. And we can test this by creating what's called a salience map, which just shows basically changes in contrast from light to dark areas in a scene. So here's a salience map for the image on the left. And individuals tend to focus on areas of high salience. And this, this kind of makes sense. We want to look at things that are interesting, right? And the sky, or the beach where it doesn't meet the ocean is just not that interesting. We already know kind of what's going to happen there. And this idea leads me to my next point, which is that we can apply top-down information to this process of shifting attention to overtly moving our eyes around scenes. And this study sort of nicely makes that point, right? So if you look at this scene here of a kitchen, in your mind you activate what's known as a scene schema. So you have some sense, you have a model in your mind of what items should be in a kitchen. So when you look at the stove and you see a pot on the stove, you don't spend a lot of time looking at that pot. You don't pay a lot of attention to that pot. And so you might only look at it for, 400 milliseconds. And that's because, that pot is consistent with your scene schema. It fits the mental model you have for, what items should be contained in kitchens. But look what happens if we replace that pot with something that's inconsistent with this mental model you have in your brain of what kitchens should contain. So if we replace the pot with a printer, we find that people spend a lot more time paying attention to that unusual item because it seems out of place. And so this is an example of a top-down influence on changes in attention. Right? You're attending to this item for longer because it doesn't sort of fit with your prior knowledge about what scenes should contain, what this scene should contain. We can also look at how we move our attention around scenes when we're performing a particular task. And what we find is that eye movements are really influenced by the demands of the task that we're performing. And when we're performing a task, we focus on things, we attend to things that are relevant for the task, and we ignore things that are not relevant. Right? So this image shows, fixation points for somebody assembling a peanut butter sandwich. And what we see here, right, is that the individual fixates on, the different components, the different parts of that sandwich in the order in which they're actually accessed. And in fact, we know from some very cool eye tracking studies that during task performance, attentional shifts are actually predictive of upcoming movements. So this is a very cool study done by Randy Flanagan. He's a professor at Queen's University, and Roland Johansson, who is a professor, I believe, in Sweden. And it involves a very simple task, block stacking. And so in this study, they had participants stacking blocks, and they tracked their eye movements while they stacked blocks. They had participants watch an actor do the same task. And they also had participants watch blocks being stacked by themselves, so blocks sort of floating through the air, a task that the participants had no experience with. And what they found were that eye movements were predictive in the cases where people stacked blocks. So their eyes predicted where they would grab the blocks and where they would place the blocks. Eye movements were also predictive when they watched other people stacking blocks, right? So you're using your prior knowledge of how blocks are stacked, how you would do the task, to predict what other people are going to do. Interestingly, eye movements were not predictive when they watched blocks floating through space. So there's some really cool video that Flanagan and Johansson have of participants performing this task. And where the eye is fixating, where attention is focused in the video, is represented by a little white cross on the screen. And again, the takeaway message here is that eye movements are actually predicting the task at hand. So stacking blocks or watching somebody stack blocks. And when I say predicting, I mean that they're sort of fixating on future grasp sites, so where the participant will grab the blocks, and also fixating on future sites for where the participant will place the blocks. So I'll show you the video. And so here we're seeing somebody stack blocks, and again their eye movements are reflected by that white cross. You can think of that as, where they're paying attention. And as you can see, their shifts in attention are predictive. Here they're watching somebody stack blocks, and again, their shifts in attention are predictive of what's going to happen. And now here they're simply watching blocks float through space, and their shifts in attention are no longer predictive, because this is kind of an unusual task, right? You have no experience with watching floating blocks stack themselves, and so in this case you simply track where the blocks move. And so the takeaway message here is that, when we're performing a task, we shift our attention in a way that's predictive of the demands of the task. And this applies both when we are performing a task and when we're watching somebody else perform a similar task. So what does attention do for us? What's the benefit of attending to our world? This may seem like a kind of silly question, because as we saw with the dichotic listening studies, right, when you're not attending to things, you don't fully perceive them. So we have some sense that, attention facilitates perception. How do we actually measure this in the lab? Well, a very famous task to get at the role of attention and perception is known as the Posner cueing task. And this task was invented by Michael Posner in the 1970s. And the idea here is that you're simply staring at a fixation cross on a screen, and you have to respond as quickly as you can to stimuli that appear on the screen. So a star to the right or left of the fixation cross. And on some trials, you're actually cued to attend to the location in space where the stimulus will appear. Right? So you're fixating on a cross, and you get a cue, a little arrow, that tells you to covertly shift your attention to the right. And then sure enough, a star appears in that location, and you respond. You press a button and say, I see the star. So these are called valid trials. Sometimes, though, that cue actually throws you off. So in some trials, you're staring at that fixation cross. You see that cue, and it says, covertly shift your attention to the right, and then the star appears on the left. And you respond, and you indicate that you've seen the star. And so what Posner was interested in was, does the cue, when it's valid, facilitate your response? And when it's invalid, does it hinder your response? But let's try the task. So here's a little demo of how the Posner cueing task works. Normally this would be done with a button press, but I'll simply ask you to raise your right hand if you see a star on the right, or your left hand if you see a star on the left. Keep your eyes on the fixation cross. So this task is based on covert shifts in visual attention. So you shouldn't be moving your eyes. Your eyes should be fixated on the fixation cross. So here we go. Again, raise your right hand if you see a star on the right, and your left hand if you see a star on the left. Okay, hopefully everybody has their right hand in the air. Let's do another trial. So that was what we call a valid trial. The cue led our attention to the right location in space. Okay, hopefully your left hand is in the air. So that was an invalid trial, right? The cue pointed us in the wrong direction. And another valid trial. So if we were to do this task over and over and over, as Posner did in many participants, we would find that on the valid trials, where our attention is drawn to the location in space where that star will appear, reaction times are actually facilitated. So they're actually quite fast in this case. On the other hand, on the invalid trials, where our attention is drawn to a location in space where the star actually doesn't appear, reaction times are slowed down. So what's happening here is that it seems like attention is actually speeding up, facilitating visual perception. Right? If you're attending to a location in space and a target appears there, you're faster to respond to it than you are if your attention is elsewhere. So attention seems to facilitate perception. And this is true, in visual processing, in auditory processing, in somatosensory processing, touch perception, for instance. Attention seems to facilitate perception in all of these domains. So paying attention is beneficial. How good are we at dividing our attention? Well, this was studied by Schneider and Schifrin in the 1970s, and they developed this task where they had participants remember target stimuli, so 4 numbers. You can see them on your screen now, 5, 9, 1, 8. And then they were shown a series of test stimuli that consisted of both numbers and letters. And these test stimuli were presented very, very quickly. So flashed on the screen very, very quickly. And participants had to do 2 things. They had to remember the target stimuli and scan the test stimuli to see if they contained any of the target stimuli. So you're doing 2 things at the same time here. You're dividing your attention between remembering the target stimuli and scanning the test stimuli to see if they contain the target stimuli, and then at the end you have to indicate, how many target stimuli did you see in the rapid series of test stimuli that were flashed at you. Very difficult task. Let's do it now. So remember these target stimuli, 5, 9, 1, 8. And you're going to see some rapid test stimuli flashed at you in this red square here. So here we go, 5, 9, 1, 8. Okay. How many target stimuli did you see in the test stimuli? And hopefully your answer is 2. So 5 and 8 appeared in the test stimuli. And what Schneider and Schifrin found was that people are pretty bad at this at first. So they're only at about 60% correct at first. But if you do this task over and over and over again, your behavior becomes somewhat automatic. And we call this automatic processing. So participants began to respond without having to consciously think about, what the target stimuli were that they initially saw. And so we see after about 600 trials, right, their performance is actually plateauing at around 90%. So they're doing pretty well. And for some tasks, we're able to repeat them over and over and over again, and we get so good at them that we can do them automatically, right? Driving a car is one of those tasks. We can drive a car and do other things. Now, you shouldn't do that. I'll show you some data in a second that suggests that you shouldn't do that, but you can do it, right? You can get away with that. Most people, drive cars and listen to music or listen to a podcast. What you shouldn't do is talk on the phone while you're driving. Now, you can't learn to do all tasks automatically. So when Schneider and Schifrin made their task harder, so in the version of the task I just showed you, the test stimuli contain both numbers and letters. You can make it harder by having the test stimuli contain just numbers and just letters. And so imagine you have to remember 4 numbers and then search for those numbers through a rapid series of test stimuli that are also numbers. Very difficult task, very challenging. And in that case, people actually don't improve at the task. They don't come to do the task automatically. They're not good at dividing their attention when it's that challenging. So there are some tasks where you never hit this sort of automatic level of processing that allows you to do the task while doing something else. So let's look at the case of driving. And this is an example, where we probably think we're pretty good at driving while doing other things. And, I think in the case of driving while listening to like a podcast or listening to the radio, that's fine. We're probably able to do that without any sort of detriment to our driving ability because, you don't really have to devote a huge amount of your attention to listening to music or listening to the radio or a podcast. Talking on the phone, though, is very detrimental to your ability to drive a car, even if you're talking hands-free. And so, we've all heard of the idea that you shouldn't text and drive, obviously. That involves, actually overtly looking down at your phone, which is terrible, right? But talking on your phone, even hands-free, is detrimental to driving, as was shown in this 2001 study by Strayer and Johnson. And so in this study, they looked at the fraction of red lights missed in situations where people weren't talking on their phone versus situations where they were. And participants were twice as likely to miss a red light, so potentially go through a red light while talking on their phone. And again, this includes hands-free phone talking while driving. So don't talk in your phone while driving. Similarly, reaction times to lights, to traffic lights, were significantly slowed for drivers when they were talking on their phone compared to not talking on their phone. And so you may look at this chart and think, well, 530 milliseconds versus 580 milliseconds. What's the big deal? Well, that 50 milliseconds, right? It could be costly. That could be the difference between a severe accident and just a minor accident, right? So the takeaway message is, if you want to talk on your phone while driving, pull over, make the call, and then continue driving. Don't talk on your phone while driving, even if it's hands-free, because it affects your ability to drive. Generally speaking, we're bad at doing two things at the same time, even things that we're pretty good at doing. Failures of attention. What happens when we fail to attend to our world? So there's one phenomenon that's been highly studied known as inattentional blindness. And the idea here is that we have a lack of awareness of stimuli because our attention is directed elsewhere. So we're so engrossed in a task, we fail to notice something else happening. So we can do a quick demo of this. We'll see if this demo works. It doesn't always work, but the idea here is that you're going to see two lines, and I simply want you to indicate whether the horizontal or vertical line is longer. And you can just shout it out. If the horizontal is longer, say horizontal. If the vertical is longer, say vertical. People might think you're weird if you're in the library. That's fine. You can just say that Professor Lametti gave you permission to shout things out in the library. Here we go. So, horizontal, vertical, horizontal, vertical, vertical, I think. I missed that last one. Horizontal. And so the question here is, I don't know if you noticed this, but a square was flashed on the screen. And if you didn't notice that square during that task, it's because you were so engrossed in this horizontal versus vertical line task, right, that you were effectively blind to what was going on around you. And what we know is that inattentional blindness like this depends on task difficulty, right? So we can apply perceptual load theory to the idea, to this notion of inattentional blindness. If you're doing a task that is sucking up all of your attentional capacity, you're more likely to show inattentional blindness. You're more likely to be blind to things that are going on around you, right? So think about that situation where you're like engrossed in a final exam and somebody gets up to go to the bathroom, slips on a banana peel, falls, and nobody notices because they're, so engrossed in what they're doing. That is an example of inattentional blindness. Probably the most famous example of inattentional blindness is a study that was run at Harvard, and I'll show you video from that study. You'll remember the study from intro psych. You'll be asked to do something, count the number of basketball passes, and I'll just ask you to follow the instructions.
Count how many times the players wearing white pass the basketball. How many passes did you count? The correct answer is 15 passes. But did you see the gorilla?
So I suspect everybody in the class has seen this video before, and so it probably didn't fool you and you probably didn't show inattentional blindness. But when the study was first run at Harvard, Simons and Chambris, maybe it's Chambry, found that 46% of Harvard undergraduates failed to notice the gorilla because they were so focused on this task, counting the number of basketball passes. And so it's a demonstration of this phenomenon that we call inattentional blindness. And again, whether you show inattentional blindness, whether you're blind to what's happening around you, depends on how difficult the task is that you're engaged in. It's perfectly predicted by perceptual load theory. If the task is very difficult, then you have less attentional capacity to notice things happening around you. So another cool sort of attentional phenomenon that I talked a little bit about in intro psych is known as change blindness. And change blindness looks at difficulty in detecting changes in scenes. So for instance, continuity errors in films. And change blindness is based on sort of manipulations of attention. And indeed, magic is effectively based on change blindness. So it's effectively based on drawing your attention somewhere else so the magician can actually, pull the rabbit out of their hat, so to speak. So one effect that's been studied is saccade contingent blindness. So again, a saccade is a movement of the eyes. And what they found in this 1996 study was that if they flipped the hats that these two men were wearing, in these images, while participants were mid-saccade, so while they were moving their eyes, 100% of participants failed to notice the hat change. So this is a really strong demonstration, right, that if you're not attending to your world, in this case because your eyes are moving, you miss somewhat dramatic changes in things that are happening in your world. Change blindness has been studied using this paradigm, so it's called saccade contingent change blindness. And again, the idea here is that two pictures that are very similar except for one thing are flashed at you, and in this case the change occurs, the flash occurs while your eyes are moving. Another paradigm that's been used to study change blindness is known as the flicker paradigm, and we'll talk about this study at length in this class, but I'll show you an example now. And so what you're going to see, and you'll remember this example probably from Intro Psych, but what you're going to see are two images, and they're identical except for one major change. It's about 10% of the image, and you're going to find that it's very difficult to notice that change until your eyes actually fixate on the changing location. So if you haven't seen this before, you may actually be struggling to see the change, and I will let you struggle for about 10 more seconds. So you're probably scanning around the scene thinking, Professor Lametti is nuts, nothing is changing, and then I will direct your attention to the airplane's engine, and you will be very shocked that you missed that quite dramatic change. And so change blindness, what it's telling us, right, is the role of attention in perception, right? If you're not looking at a changing element, you actually literally do not perceive the change. So we need to pay attention to our world in order to perceive it. And as mentioned, we'll talk about this paradigm, the flicker paradigm, at length in this class. We'll discuss the original paper, which is maybe, quite possibly, my favorite psychology paper of all time. It's a beautifully written paper. Take-home message, you have to attend to your world in order to perceive it, as change blindness shows. Okay, we've come to the lecture review. Question 1, what's the difference between an overt shift of attention and a covert shift of attention? Easy question. Overt versus covert. In an overt shift of attention, you move your eyes. In a covert shift of attention, you do not move your eyes. So that's the central difference. Question 2, what does the Posner task demonstrate? So the Posner task, sometimes called the Posner cueing task, what does it demonstrate? Question 2, what does the Posner task demonstrate? You respond to stimuli faster if they appear in an area of space that you're attending to. That is, attention actually speeds up the processing of sensory information. Very important idea. Attention speeds up the processing of sensory information. Question 3, what is inattentional blindness? Question 3, what is inattentional blindness? And students often confuse inattentional blindness with divided attention, which is something different. But the idea here, right, is that you're not aware of stimuli, not aware of things happening in your world because you're so focused on a single task, right? Counting the number of basketball passes in a group of players throwing around a basketball. And whether you show inattentional blindness depends on the difficulty of the task, as predicted by perceptual load theory, right? If the task is very difficult, you're more likely to be blind to other things in your world. And what this task shows in combination with change blindness, right, is that you need to attend to your world, to things in your world, in order to fully perceive them.